today we're going to do some novelty soldering. So I've been using this method of rapidly prototyping circuits using bare pieces of FR4, in this case double-sided, to make simple circuits that I don't want to take the time to design a circuit board for. They might use surface mount components, so they're difficult to do with perf board. It's kind of a different way of doing things. I've never gotten into home etching. I don't have the ferric chloride and so forth, and I cannot afford a PCB mill right now. Not to mention the fact that they're rather loud. So this is the kind of stuff I'm talking about. This is a remote I made for a Nikon camera, so it's pretty simple. I don't know if you can see the little pink LED lighting up, but this LED is an infrared device. It will shoot a beam about 35 feet. The trigger my camera just uses a Atmel AT9044 processor to actually create that waveform pattern. I made a little current shunt resistor setup for measuring the current draw of another project that uses these JST connectors. So really fancy resistor, really cheap construction. There's another project that I did. I posted a video about it earlier, but basically it's got a bunch of LEDs on it, a couple of shift registers. Some of this was done in midair, which is really just for the hell of it. But you can kind of see the construction method on the board at the base. Essentially, we're going to be taking a razor blade and slicing up the FR4 program. So I'm using a cheap GoPro, so I apologize on the video quality. It should be adequate. I'll see if I can find my resistors at some point. So to start with tools, I've used a lot of different kinds of razor blades. The Olfa narrow model snap-off is the one that I've come to prefer. It comes with this handy blade container, so it's got, this has I think 10 spare blades in it, but you can also use the opening here to snap off a fresh edge, and then it stores it safely. You'll be doing that a lot. You know, this is not a process that's common on razor blades, so it's worth having a quick way of getting a sharp edge. This is a little attachment I made for my razor blade using a XT60 connector from another project. Just allows me to put a lot of pressure down. It's not perfect. They probably make something like this. I think it's something that they probably should 3D print in the future so it doesn't slip off as easily, but it really helps with the fatigue factor. This will come in handy during the soldering step. You know, you need to use flux. I use a ton of flux. Because I use flux, I also use a fan to blow the flux fumes away from my face. I use a Rojas, mostly tin with some silver and some copper, .02 diameter solder from a company called Chip Quick. You can just let it solder too, of course. You're going to be able to drop the temperature about 100 degrees if you do that and generally have a nicer time, but it is what it is. Tweezers, you know, I have a couple sets. I'll probably be using these straight ones most of the time. A anti-static brush and some isopropyl alcohol that will be used for cleaning the flux off at the very end. A couple of flush cutters, and then some more heavy-duty diagonals that I'll use for trimming some parts. Let's see, I think that about wraps it up for tools. I do have a vise. I'll probably be putting the board in the vise when I'm doing the soldering. In terms of materials, I have this 34 gauge magnet wire. I like this stuff because you can touch a tinned iron to the tip of it and it just burns away the insulation. It's very fine, so you can use it for fine pitch stuff. In this particular project, you know, with this Blinky project, you know, I used a lot of that, and I really had to because of space constraints. For this project, you could probably use a thicker wire, but I'll probably mostly be using that. I also have a couple scraps of some 26 gauge stuff that I'll use for some of the power connections. I do have this piece of FR4. As you can see, I've cut some pieces out of it. This is still perfectly good. You can go pretty far with a piece of FR4. So what I'm going to be doing is making the circuit kind of off to one side. Of course, I forgot my tin snips, so I won't be able to cut it out right now. But I'll do that probably off camera and then post another follow-up video after I write the firmware and actually do the upload and show you what the finished product looks like. So, and then I'll probably add that onto this video so you can see what the finished product looks like at the beginning of the show. So the FR4, then I have a bunch of parts. These are all the parts for the circuit. I guess this is a good time to tell you what we're going to be making. This is mostly just based on stuff that I have in my junk drawer. So these are 580 nanometer LEDs, which is kind of a pure yellow. 0402, 2.1 volt drop, 20 milliamp, pretty standard stuff. Rome's Pico LED series. I like these a lot just because they're tiny and it adds an extra, kind of an extra angle into the project. 0402 stuffs can be a little challenging. 0.1 microfarad bypass capacitors, I'll just use one of those. 10K resistor, this will be used as a pull-down resistor for the switch. Yeah, I could wire the switch the other way and use a pull-up resistor, which is built into the processor, but I'm not going to. So, and then these are 150 ohm current limiting resistors for the LEDs. This whole thing's going to operate at 5 volts, so 5 minus 2.1 is 2.9 divided by 0.02. That's 145 ohms. So these will be just about right for driving the LEDs at 19 milliamps or so. I'm going to be powering this circuit with a pair of CR 2032 batteries. Coin cells. I bought a whole bunch of them, and because of that, they've been finding their way into a lot of projects. They're pretty handy, very cheap if you buy them in bulk. So I'm going to be using two of those in series to get me 6 volts. So I have these two battery holders that we'll be using. Then, again, we could just run it off one and not use a regulator, but I have the regulator, so I'm going to be using this kind of oversized 1 amp SOT 223 low dropout regulator. Because of that, I have a 6.8 and a 10 microfarad tantalum capacitor that will be used on the input and the output side. Read the data sheet. You look at the reference diagram for using this regulator, and it says to use those two capacitors. So that's what I do. Very simple. This is a switch. I'm going to use it as a hard on-off switch, just so I don't waste power when the thing is not running. It's DP/DT, but I'll just be using 2 of the terminals, and then the rest of them just as reinforcement. Here's a switch. I'll be using that as a single input. And here's the processor. It's a ATtiny 44A in a SOT 23, a SOIC package. So pretty simple to solder. I think the spacing on this is 0.8 millimeters. You can do 0.65 with this method, but 0.8 is really the limit of what's really sane. Like here's some 0.65 spacing shift registers, and you can see that it's quite a difference. So that's the processor we'll be using, and what we're actually going to be building is a little two die board game assistant. So it'll be using the LEDs. I'll make the 14 pips for 2 dice, 1, 2, 3, 4, 5, 6, and then this button will be used to roll them. And in software, what that'll do, this will just have, when you hold this button down, it'll just really quickly cycle through all the possible combinations, potentially in some kind of a random fashion. Then we release the button, it just freezes on the last one. So kind of a pseudo-random type of setup. And then since we have 14 LEDs and we don't have an FIO lines, we'll be multiplexing them. To make the firmware a little bit simple, I'll be doing a 7x2 multiplex. I'll be 9 IO lines. So I don't lose them. This stuff goes back in the non-anti-static parts storage compartment. So those put away. I really should have printed out stuff, but I don't, because part of this method, one of the advantages is that you can really just kind of throw stuff together at will. So that's what we're going to be doing. This is the ATtiny 44, just a basic pinout diagram. So VCC and ground, I'll be putting a bypass capacitor between those two, very close to the board. Otherwise, I have the port B registers, PB0, 1, 3, and 2. And I'll be using probably PB0 for the switch, PB1 and PB2 for the the commons between the two die. PV3 is the reset, so we're not going to mess with that. We'll just be putting a wire on that for programming. And then the port A register, we'll use 7 of the 8 of those, for probably the anodes of the 7 LEDs. Pretty straightforward. We're not going to be getting to that for a little while though. So the first step is going to be kind of doing a general layout plan. This is double-sided FR4. The advantage of that being we can save a little bit of space. I certainly don't drill any holes in that because it's a pain. So we're going to be wrapping wires around the outside, kind of similar to this with this little project where you just wrap a wire around when you need to connect to the back to the front, and you put the battery and the power supply stuff on the back, and you put all the logic and LEDs in the front. So first thing with these holders, I found it's nice to just trim the wings off of them. They're not any more difficult to solder, and frankly they have more than adequate mechanical strength, and you save a couple millimeters on each side, and it makes your project a little smaller. Most of the stuff I do is pretty tiny, and these battery cases end up being kind of the limiting factor. So the backside here is actually going to have a fair amount on it. We'll put the 2 batteries probably like that. Important to remember that with these batteries, the really big part is the anode, and then this little tiny part is the cathode. So a little bit counterintuitive. We'll probably put the batteries right next to each other, although we do have to have a gap in there, so we'll go from one to the next. And then we'll get the LDO. We'll put the switch in. This is one thing that I've done in the past, is I actually put the switch between the 2 batteries. So you're still breaking the circuit. And then we'll have the LDO and its associated capacitors right here. I have to remember that the 6.8 microfarad. All right, battery died on the GoPro, now connected to external power, so it should be good. Anyways, where were we? LDO, 2 capacitors, 6.8 microfarad goes on the input on the VN side, which is the larger capacitor for some reason. So that'll probably go something like this. Maybe I'll put it around like that. And then, yeah, that'll work. The stripe is the anode on the capacitors, and then the ground is the middle pin, and that's connected to the ground pad. So yeah, I like that layout. I think that's reasonable. That means it will basically be just cutting off this part. It'll give us a decent amount of space on the other side too. So, all right, before we actually start cutting anything, we'll just give a quick thought to this part of the layout. I think what we'll probably do, just in the interest of symmetry, is have the processor right above the button, and then we'll have a bypass capacitor right here between pins 1 and 14. This will jump right into one of the port B registers, so that'll be probably right here. We'll probably do a big ground plane so that we can easily do a pull down resistor on the other side. And then the LEDs will go, bing, 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 on either side. So I think what we're gonna do, since we definitely have more than enough space for that, I mentioned before that I left my tin snips at home, unfortunately. So we'll just use a marker for now, so we can draw the boundaries of where this is all going to sit. I just need to find something that has a straight edge on one side. Kim Wipes box, perfect. Sort of. All right. I have a tendency to try to make things as small as possible, which is really dumb. Like, just make it just a little tiny bit bigger, man. Like, no harm, no foul. No one's gonna criticize you for making something a tiny bit bigger. So like, the old Zach would probably say, oh man, I could put these right next to each other, and then I could stash the switch in there and the LDO, and I could chop an inch off one side, and then it would just be a nightmare to wire and solder. So I'm gonna leave a little bit more space than that. I think I'm gonna put these kind of like that. I'll have the switch nice in the middle right here, and then the LDO and stuff will go on the end. And I will plan to not chop any of that off. We'll just leave ourselves plenty of space. All right, so first step is going to be just cutting the board up, and we're going to want to try to do as much of that as possible in advance. Certainly before we solder anything. I try to solder the battery packs first because they have the most thermal mass, and I tend to need to turn my soldering iron up, usually to 800 degrees Fahrenheit to get those to really sit right. Because of that, I don't want to have other stuff soldered on there because I don't want to damage it, although that's really never been a problem. And then once you have anything mounted on the board, it just becomes more difficult to cut things because you really have to put a lot of pressure down when you're scoring the FR4, and you don't want to potentially damage stuff, especially things that are mechanical like the switch or these battery compartments. Once we solder them down, if we flip the board over and then start cutting on it, we'll probably bend them, and it'll just be a pain. So what we're going to do for right now is just cut the outlines for these. Again, the outside is positive, the inside is negative. So the first thing we'll do, we'll just mark where the boundaries of this battery case are, like that. So we have kind of a rough outline. You can kind of put little scratch marks in the FR4 in the copper without really damaging it. You don't want to do that too much. You certainly don't want to cut through it where you want to have a connection, because then you'll have to put a jumper in, and that just looks silly. So 2 battery cases will kind of go like that, and they'll basically extend from the top to the bottom. The way these battery cases sit, they push down on the positive side, and the negative side is in the middle. So what we'll want to do is basically take the negative of this one over to the positive of this one. So what we're going to do is kind of cut a little box shape like that. Cut it down at an angle, and then just have a straight line that goes over here. Oh yeah, and we want to put the switch in. So then the switch will get soldered onto that, like so, and then that'll just kind of slice down. You probably can't really see these scratch marks. I apologize for that. So it goes. Yeah, and then we'll have a barrier here. And this will be the positive rail come across. Okay, so we'll start committing some of this stuff to copper. The general idea when you're slicing this, let's do a little cross section. So we have FR4, and we have a layer of copper on each side. What we want to do is cut at an angle entirely through the copper, and then at an opposing angle like that. So we're gonna end with a little groove in the FR4, which you can very clearly see. Well, maybe not so clearly see in these. It tends to collect flux residue and just get disgusting. So you really have to scrub it out when you're done. But we want this clearance to be adequate, that any extra like burr that rolls up on that doesn't have a chance of bridging the gap. So you can make it really small. I mean, like, you really don't have to make it large. The thing to remember is that you are going to be doing 2 different cuts. If you just try to do one cut, you'll kind of curl the material up, and then it'll potentially bridge itself and create a short. So I try to aim for maybe 0.5 millimeter wide, 0.5 millimeter is written upside down. Yeah, you'll get the idea after I've done a few. We're saying always wear your safety glasses. You know, this stuff shouldn't really fly too much, but your eyes are the kind of the most valuable tool you have, so don't mess with them. And then the fragments that this tends to create are a little bit nasty. I mean, they're basically fiberglass with a little bit of copper on the top. So just want to make sure that you collect them and don't let them get on the floor or whatever, get in your food supply. You know, those are all bad things. So what I'm doing, see, I'm at like maybe a 30-degree angle. I'm just putting a decent amount of pressure down and following the contours that I developed previously. And I'm only doing it on one side right now because I'm left-handed. My right hand is essentially worthless other than dispensing solder and holding the board down. So what I'll do is I'll just turn this 180 degrees when it comes time to, you know, to cut the rest of that away. Switch will go there. And then we want to isolate that other side from the positive rail. It's worth mentioning, you know, if you mess up, you know, if you cut over something that you really didn't want to cut over, it is not a big deal. All you have to do is take a little scrap of wire and bridge a gap. It's hard to do that with solder. You try to do it with solder, you're probably going to screw it up. It's going to look pretty bad. But you know, if you just do it with you know, with a little bit of wire, you know, everybody will think that you did it on purpose, even though if I look at it, I will know the truth. So yeah, there's our first little bit cut successfully. You can always touch these up too, you know. You can always go back and just take a little bit more material off if you think you need to. Kind of ironically, you know, when your knife is brand new, you really have to be careful that it doesn't, obviously so it doesn't slip and cut your finger off, but also so it doesn't kind of push its way out of the groove and make the track wider than you wanted, or, you know, kind of the knife kind of is in control when it's super sharp, which is a little bit annoying. There we go, that's a good one. You can kind of see, you do get a little dust. You want to be careful of that dust. Brush it out of the way, wash your hands when you're done. But you'll get this little rolled up bit of copper. You can just kind of pluck that up off and put it in a little pile off to one side. Should go without saying, you know, just be careful when you're doing this. Don't put your thumb directly behind where you're cutting. You will have a bad time. I've never gotten a serious injury doing this because I've always been really careful. So always be really careful, and you will not get a serious injury while doing this. One of the things I really like about this technique, well, other than the fact that it kind of forces you to work with your hands, and I don't know, it's kind of relaxing, is that you can, you know, you're developing this circuit kind of in real time. You're not doing a lot of advanced planning, which, contrary to popular belief, is a lot of fun. You just kind of do what you want. Okay, so now I want to just make sure, you know, I'll basically take let's see, the switch is going to go in here, so I want enough clearance for the switch. And this battery holder will kind of be located right there. So then the cutoff point for that is about right here. So we're going to have our positive rail. It's going to be up top here. It's going to come through like that. So I'm just going to cut that trace just so it's very clear. This is the part that gets really painful if you don't have a finger rest. It's really probably actually bad for your hands if you're pushing down on that ridiculously narrow part of the razor blade. And don't even mess with X-Acto knives. You know, I used to use one of those. The blade's just way too thin and floppy. You know, you need something that doesn't have a lot of blade sticking out and has a moderately thick blade that you don't have to be crazy paranoid about not dulling as well. Obviously, I'm cutting through fiberglass. I mean, the copper is not a big deal, but you know, you're rubbing the tip of the knife along this fiberglass surface, which is certainly not good for sharpness. But probably still have a lot of life left in this blade. I usually, a project like this, I'll probably go through 2 or 3 snaps on the blade. All right, so that's going to sit like that. Switch is going to sit like that. Battery holder on the other side will sit like that, and we will be doing some Kapton tape insulating, which will just prevent short circuits. But we'll do that later. So this guy is going to come down like that. This will be our ground, our negative going into the regulator. So let's see. And then of course this whole area is kind of an intermediary. So yeah, we can actually get rid of that and just go like this. And this whole thing will be a ground. That'll be great. And we'll throw some tape on there just to make sure it's not going to short out the battery. You can see I'm already not going to be using this trace right here, so that's why doing the advanced layout is important. But pretty much every project I do like this, there's at least one trace that I accidentally cut, and then I just have to put a little bridge in, which is fine. See if anybody actually hears any of this audio. There's a good chance when I'm doing the cutting work, I'll just put it in high speed so you guys don't get too bored, or maybe not. We'll see. Yeah, that was my finger guard slipping down a little bit. So it's not perfect. Like I said, I should really 3D print something. I like the fact that it's removable and it kind of is contoured to fit this, but you know, the fact that it slips down is a little bit of a pain. All right, so, ooh, this is one thing that I forgot. That little bit right there needs to be soldered down, so it needs to have its own little soldered area. Yeah, so what I'm gonna do actually is just give it an isolated spot. It's a little high risk because I didn't actually measure anything while I was doing that, but I think we're good. Yeah, so that's not going to be electrically connected to anything. I just wanted to make it big enough so that it doesn't, it doesn't rip off, and so on and so forth. Again, this is one of the reasons that I trimmed those wings down, so I just don't have to. I don't have to sacrifice as much space for structural support. Yeah, this will be more than enough. Not something you have to do. If you don't want to trim the battery containers down or the battery clips down, don't trim the battery clips down. That is a-okay. Whatever you do not trim the battery clips down with your nice, fancy, expensive side cutters. Do it with the old, beastly Fuller ones that you inherited from your grandparents that can cut through anything. Use the right tool for the right job, right? All right, battery clips. Battery clip 1 goes like that. Battery clip 2 goes like that. Of course, it's very important that everything is very symmetrical. It looks like it's good. So the one area of concern that I just want to make sure I don't mess up is I soldered that side down. I want to make sure that I don't get inside this line. One thing I didn't mention before, everything I do, I tend to continuity check before I actually solder anything. So you just do continuity checks between pads that shouldn't be touching each other, and I've never had one fail after I've done that. I've lost a few continuity checks, in which case I just get the razor blade out and tweak it a little bit, and then everything is usually fine. All right, so this is kind of interesting. I have my ground here. I have my 6 volts here. So what I think I'm going to do is mount the LDO like this. So 6 volts on that side, 5 volts on that side. Maybe I'll push it up a little bit. Remember, the 6.8 microfarad capacitor is smaller, so he'll go like that. And then, you know what, I'm going to move this whole thing over a little bit just because I made a commitment to not trim this board at all. So you have this tendency to just want to bunch everything together. It's like, no, don't do that. You don't have to do it. Give yourself plenty of space. You got enough challenges with this rather bizarre circuiteering methodology as it is. So when I do an LDO like this, what I'm going to do, since the middle pin and the tab should be connected, and those will both be connected to ground, which is right here, what I'm kind of do is go down, whoop, make it nice and wide, like that, and then take it back, like that. And you know what, this is, I'm going to actually just take this one over straight down. And that guy, take it reversed. You can sit like that. You know what? No, I'm not going to do that. And then this will fan out a bit for the tab. So now we have ground going through. I don't need 6 volts anywhere anymore, so I can actually just take this straight back and then drop the capacitor across like that. Let's see, but I do want this output to be accessible, so I think what we're going to do, take that at the diagonal, maybe take it back right here. Then I will have the option of putting the capacitor in one of a couple different places. Excellent. All right, before you think about it too much, get cutting. Alright, let's see, where does this one go again? Okay, it's the ground. Ground comes down, up, over, and back. Get a cutting mat. Forgot to mention that. That is an important tool. I destroy cutting mats, but they tend to be pretty durable. Pretty useful things too. I tend to use it as a work surface for all sorts of stuff. You can see this yellow tape residue when I do stencil work. Using a Kapton stencil for applying solder paste to a printed circuit board, I will often use this as my working surface. So I'll constantly taping stuff to it. So because I use cheap tape, the residue gets everywhere. It really just becomes disgusting, but that's fine because it still gets the job done. Okay, I think this is this side actually complete. You know, might not be super obvious right now, and again, I am going to insulate a couple strategic spots with Kapton tape, but this should give us a switched 5-volt power supply with all the discrete components that are required. Just double check some wiring. So positive goes over there, negative, switch, positive, and then negative. Get this LDO in place. LDO again stands for low dropout, so just still a linear regulator, a little bit more efficient than a 7805 or something like that, one of the old school ones. This capacitor is just going to sit right there. This one, I think we're going to stash this capacitor right here. And then this will have a loop going across here. That'll be our ground, and then we'll have a loop going across here. That'll be our 5 volts. So we're going to mark those. Those will be the only two side-to-side vias, if you will. So we'll just mark those so that it's easier for us to remember what goes where on the front. So G, and then we'll just infer that the other one is V++. Cool. I'm gonna go grab my multimeter and we'll, you know what, no, I'll do that later. Let's get the other side carved up. So we're gonna put all these away, blah, blah. It's all well and good. Things are awesome. And so this side of it, the other side, I tried to do basically all the wiring using traces, and it was pretty easy because it's a very, very, very simple circuit. I was just able to cut away strategically and do that. On this side, I probably won't have that luxury, and you can really spend a lot of time trying to figure out how to get stuff all traced. So, like in this case, I was really diligent about trying to avoid using any jumper wires, but because we're going to be doing multiplexing and we're taking, we're going out to all these LEDs and so forth, we're just not going to mess with that. The best thing I can do is position the microcontroller in such a way that the pins are accessible. It's pretty easy to get to everything and actually run wires out to it. And then I'll just use lengths of this enameled copper wire. And maybe I'll flatten everything out after it's all programmed and tested and polyurethane or something like that. So it's a little bit more durable. I've done that in the past with some spray on, and it seems to work like a charm. So let's see, we kind of want to put this guy in the middle. We'll put the switch at the very bottom so we have just kind of as much breakout space as we can. Maybe it makes sense to do it like that. Nope, I'm going to do it like this. Getting back to our handy pinout diagram, we can see that on the ground side, here's PA 0, 1, 2, 3, 4, 5, 6. So those are really going to be, port A is going to be going out to the 7 LEDs. So I think we want it oriented like that, roughly centered, so on and so forth. Put the bypass cap there, dropping resistor over here. We'll put a slice down the middle of this to separate the two sides, and then we'll branch off from there. I think everything else we do is going to be discretely wired. So we'll probably have a pad here where we can pick up the ground. We'll have a pad here where we can pick up V+, VCC, and then everything else will be kind of discrete. And then our 7 LEDs are going to go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, something like that. Yeah. So first thing we'll do is we'll just slice off the ground. We're going to be pulling ground and power to a couple different places, so we'll just have decent sized pads there. And again, I think I could have done something clever here. Like I think I could have taken some copper all the way back to the IC, so I didn't have to use wires, but it's too late. Not doing that. I don't want to mess with getting in the way of the LEDs. Effectively, I'm going to have 3 rows of LEDs. Each LED needs its own, current limiting resistor. So the wiring is going to get a little bit. I don't want to say messy, but it's going to get a little messy. So on this side, our objective is really going to be, rather than trying to build a circuit, we're really just trying to build landing spots for everything, and then we're going to point-to-point wire everything together. I think that's going to be easiest. I think the only, we might be able to directly wire in the switch and directly wire in the bypass capacitor. Definitely the bypass capacitor, you always want to directly wire those in, but I think the switch is a possibility as well. So here's where it gets kind of interesting. We're going to put these on. These switches actually cross, they switch on and off across the short axis. So we'll put it like that. And of course it has to be aesthetically pleasing, so we're going to try to keep everything in line as much as possible, and that way the user can go think. The other thing we might end up doing, just so it sits flat on the desk, is I might make a couple of wings out of FR4 and then solder them at a 90-degree angle so it kind of holds everything off the table a little bit, so you can really just press the button and be in good shape. All right. Just thinking, I might put the switch over here. That might make more sense. Maybe this whole thing will be a little bit uneven. Because we really want to have a lot of room coming off that microcontroller. Again, since we're multiplexing, all these pins are going to multiple places. So we have to make sure that we leave room for that. Yeah, I think we're going to do it like that. Don't spend too much time on any one decision. You have too many things to do. That's the rule. So when I'm doing a microprocessor like this or a microcontroller like this, I'll really just hold the device in place and put in some really, ideally, very accurate and very easy to read scribe lines. So again, we're going to have a slice down the middle, just basically breaking out the pins. See, I already screwed that up. I'm just going to have to move over just a tiny bit. If you want to be fancy, you could fan them, but then you really have to be more worried about alignment. Then I think it's better to do it kind of in a grid configuration like this. And what we'll probably do is just cut these verticals, the top and the bottom verticals, in one go, and then slice them in half lengthwise across the chip. Let's see, we have VCC here, so we'll just box that in like that. And these other ones are just I/O connections, but we'll try to be nice about it and give ourselves a little bit more space wherever possible. So yeah, these lines, that should be enough room to get, well, you probably get like 5 wires on there if you really needed to, but it'll certainly be more than enough for 1 or 2 wires per pin. So it gets a little dicey, but not too bad. Let's start with these. Really just want to make sure that you're accurate. You're going to be going really close to other connections, so just a real steady, kind of confident hand combined with a lot of just eyeballing, just estimating. Doesn't have to be perfect. These dual inline surface mount packages are pretty simple. You get into quad flat packs. It's still very much a viable method, but what I'll do then is I'll often actually partially cut out the pin arrangement, maybe on 1 or 2 sides, and then just make sure that I have a big blank area in the middle. And then after tacking down part of the IC, I'll actually continue slicing it after
after partial soldering, just because it's hard to be that accurate in advance. You must use the pins to guide the knife, and yes, it gets pretty dicey. But I've been able to do 0.8 millimeter spacing quad flap packs. I haven't tried anything more advanced than that. Certainly BGA's, QFNs, you know, this is not a appropriate technique for that kind of hardware. But you know, there isn't a lot of good stuff out there in dual inline package format anymore, unfortunately. You know, you can use a breakout board. You know, you can get them on eBay or Alibaba or AliExpress pretty cheap. That'll convert a QFN into a dip, but I don't know. I just don't do that. This is the method that I have identified as working for me, and I'm guessing it'll work for other people too. It's a little bit time consuming. It's a little bit tedious, but that's all right. All right, little guy flew over, so just get him out of the way. One disadvantage of not cutting this board yet is that I won't be able to do all of the continuity tests, which is why I'm really being generous about cutting that piece part away. Again, we're gonna part off on that line, so it's not gonna be a permanent solution, but we'll just do our crossbar, make it nice and generous. Size on that crossbar is not nearly as critical as it is between the pins. Now we'll check for fitment, see if this is actually going to work or not. This might get in the way of the camera a little bit, but yeah. Yep. You do have a tiny bit of leeway. You know, if you have one or two that are too close to one side, you can tweak pins. You know, you can push a pin maybe a couple tenths of a millimeter in one direction or another, just to kind of bend it around a accidentally curved trace, but you really don't want to depend on that method if you can avoid it. All right, so we'll do the switch now. The switch is going to go right here, and we'll orient it vertically. So this will be an easy one. We'll just get pair lines in. This will really be mounted close to the edge. I want the dead area around the switch to be about as big as the dead area around there, so we have plenty of room for the LEDs. So just go like that, like that. Still recording? Yes, excellent. Really hope the light is sufficient. I haven't invested a lot of time or effort into video equipment. This is kind of the most advanced I have is the cheapest GoPro from 3 years ago. But I think it's going to be better than my phone, although the lack of preview can be a real pain. All right, that's where we are now. I think now the next thing we need to do is lay out exactly where we want the LED elements to be. So this will just be, will this be eyeballed? If I can find my ruler, then it won't be eyeballed. All right, pausing time. All right, got my ruler. Pro tip, when you get a PCB ruler that has components on it, don't solder components to it because then it doesn't sit flat on the table. But I like soldering, so it goes. I think what we'll do, probably do 15 millimeter spacing on the die. That'll work, yeah. So not very accurate. That's okay. So that was about 4 millimeters from each edge, 3.5 millimeters from each edge. So. like I got it. Cool. So it's easier to see. A couple dots there. And then we'll just eyeball the rest of them. Nice. Seems like it'll be pretty visible, which is good. This does not have to be anything approaching exact, obviously. Just has to look reasonably like a pair of dice. Interesting. I think this was a kit that you could buy back in the day, and I want to say it used like some TTL logic in a 555, but it was the same idea where you hold, as long as you're holding the button down, the die are recycling, and then as soon as you let the button up, they stop. It's kind of the same pseudo-random type of arrangement. So the LED elements we want to have right in the middle of those dots, and then we're going to have the resistors kind of off to one side, and then we'll have decent sized pads on one side of the resistor so we can actually solder the jumper wires, and then a pad on the other side of the diode so we can solder it on the other side. You know, actually, this is going to be still pretty tight. That's okay. So the first thing to do, we're doing with 0402 stuff, so you know, this width is probably going to be about right. It gets a little tight, but it's not horrible. So I think what I'm going to do is just cut verticals for the LEDs, and then probably a vertical right next to that for the resistor, and then some cross beams just to isolate the different traces. And then we'll figure out the multiplexing somehow. It'll be great, no problem. You can see sometimes I overshoot with the cutting when, you know, the length accuracy is not critical. It's just something that you do to speed things up. Be interesting to see how long this takes. I've made a number of circuits this way before, but I've never actually videoed the whole thing, and I've certainly never timed it. Some examples like that 16 LED free air deal, Blinktronicator. I mean, I think that one took an entire day. But like the Nikon remote, you know, that was a couple hours, pretty quick. Decent amount of that goes into planning, but I'm hoping I can get this whole thing soldered together, at least carved and soldered within 2 hours. Otherwise, I think this could be a cool workshop. You know, might be enough of a novelty that folks would be interested in learning how to do it, and materials provided that soldering stations are available. The other materials, and even like these knives, I think these knives are like $8 or something. Everything else is pretty affordable. Okay, so we have our LED spots. Put the resistors on the integrated circuit side. So LED and then resistor. So the resistors will kind of be above and to the right on this side, and above and to the left on this side. Again, this is all 0402 stuff, so it's nice and tiny, which makes things really easy to a point. on this side, but I can still see those dots because this is going to get confusing. I think on this side, yeah, we'll put the resistors on the other side just for the heck of it. There will be a little bit of Sharpie residue. You'll also notice this board is filthy. I may hit it with some steel wool before soldering, but I also place a great deal of faith in flux. So I think it'll actually be fine. All right, you know, I'm just gonna cut the rest of this line. Actually, you know what? No, I left my multimeter at home, so whatever. We just need to separate here, here. So LED resistor, actually, yeah, so we're gonna want to separate all the way to here. So we need 3 pads. We need LED anode, LED cathode, resistor, resistor. Those all need to be isolated. And these 2 I need to be able to pick up wires from, so. Should be rather interesting. Yeah, you know what? We're just gonna do a grid. Grids are our friends. What I'll do shortly is, it's almost lunchtime, so after I finish cutting this, I will turn the camera off, I will obtain some food for myself, I'll swing by my house, and I'll pick up my multimeter and my tin snips, and we will return to this little shindig. Like I said before, it's a bit of a pain if you have to continue cutting stuff after you've soldered things on the other side, but it's not impossible. I think, just giving a general guess here, I think we're going to have to take, we're going to have to do that at least a little bit. You know, I'm sure I'll forget something. This is a little more complicated than I thought it was going to be. So it goes. All right, so I have LED anode, LED cathode resistor, resistor, anode, cathode resistor. Ooh, okay, so that has to be, this middle one actually has to be broken in half to isolate that resistor from that other LED's anode. Easy enough. Okay, now 402 stuff is tiny, so this is not going to be an issue. So that'll be the center, anode, cathode, resistor. Yep, another isolation right here. No problem. If you're wondering about programming, I'll be temporarily soldering on a handful of wires to a temporary programming harness, blasting out some code, and then desoldering those wires forever until I decide to improve the firmware. And then that's when I generally will break it. So I try to fix things that aren't broken. Okay, so this one is backwards, if you remember that. Anode, cathode, resistor, slicey, slicey. Boom. See, I overshot a little bit there, but nobody cares. Not a problem. All right, well, that's a disaster, but I think it's going to work. And just think, roll the dice, let go. Good to go. dropping resistor for the pull down resistor for the momentary switch. Of course, I can't find the momentary switch now, but we'll squeeze that in somewhere. I'm not too worried about it. I think we'll be able to put the switch here, and then maybe we'll take the dropping resistor, the pull down resistor. What can we do over here? How can we make this a little nicer? I think we're just going to have to take a wire from this ground all the way over. That's fine. We're going to have a ton of wires all over the place here anyways, so it's not a big deal. I'm just going to give this a quick look under the magnifying glass. See if anything jumps out. Does not take much to bridge one of these gaps, but as long as you clean up all the debris, you know, stuff tends to jump out pretty nicely. Yeah, and once we slice this off with the tin snips, we'll clean up all the edges. You can see when I do an edge, I tend to go and I really dig into the mat. And the reason I do that is because it's really easy, if you don't do that, to get a little tiny bridge right at the edge that you want to avoid, obviously. So. Yeah, we'll do some electrical testing. Come back to this after lunch. I think this is going to work. All right, so I have reviewed some footage and realized that the GoPro audio sounds absolutely terrible when the back of the camera is closed, so I had to open it for charging. That's how I figured that out. Still charging it, but I'm going to keep the back of the camera open kind of all the time now, just so you guys can hear me a little bit better. The room I'm in is a bit echoey, so deal with it, I guess. Got my tin snips, so we can cut out the circuit. You know, it's important to try to do this as straight as possible, but you know, tin snips are a bit of a blunt instrument, so we can always fix things later, right? All right, there's our circuit. Just looking at this, I can already tell that I'm going to need to clean up these lines just a little bit in some spots. Yeah, I think that'll get us. Pretty close. I also grabbed my multimeter from home. This little guy did hit it with my soldering iron, so now it's definitely mine. Just set it for continuity mode. We'll just. Wow, there's a lot of pads here to check. I usually just do the adjacent ones because they're the ones that really matter. You get pretty good at this. Oh, we got one. Got a live one. All right, so just get this guy. Double check that we're in the right one. Those two, yeah, not even close. But it was hidden, the copper was hidden by the Sharpie mark. So it goes. All right, now better. Very important to get these right now before actually soldering something down. Once you solder stuff down, the solder, as you'll see, goes a little further than you normally want because we're not using any solder mask, obviously. So because of that, and because I'm impatient, it is difficult to remove components once they are down. So we want to make sure that we basically eliminate this as a potential source of problems. All right, good on that side. So that'll be pretty easy. All right, we are good. Okay, so I think the first thing we're going to do is we're going to get the 2 battery holders down. So I'm going to get my soldering iron heated up. I'm going to set it to 800 degrees for right now because the stuff we're going to start out soldering is rather large. This board, first of all, is going to get disgusting. It'll get covered in flux, so I'll clean it a couple times. After I put all the bond, all the connection wires on, our only real way to clean it will be to kind of agitate it in a cup of isopropyl alcohol, which I'll probably do off camera. But we'll try to get it as clean as possible before we put anything delicate on it. If there's just surface mount components, you can usually just scrub those. So the way I do these battery holders, you'll notice I'm using my stick vise. If I were to leave this on the cutting mat, I'd melt the cutting mat, which I've done more times than I care to mention. The way I do these holders is I'll typically put a pretty decent size, get my fan on, put a pretty decent size glob of solder kind of right under where I want to connect to the cathode. Remember, the cathode is actually the smaller bit. So I'll get a decent glob of solder there. Doesn't have to be perfect. Again, a hot iron, really important here. And now you can just kind of take the battery clip and figure out where you need to put your insulating material. In this case, it's going to be Kapton tape, or Kapton tape, I believe it is sometimes called. Basically, we're going to want to mask off. On this one, we want to mask off the tail end of this, just so that it doesn't cause any short circuits. Kapton tape is pretty nicely temperature resistant, so we don't have to worry about that. Now, whether it's isopropyl alcohol resistant, we'll see. But we'll just kind of put a little piece right like that. So now when I put this down, the only place that cathode is exposed is where it should be. Put one more little chunk in. Love Kapton tape. Very useful stuff. Very useful. Okay. Let's go ahead and get this one soldered down, just so we have something to show for all this work. Put it like that. And what we'll actually do is we're going to, it's a pretty common technique for surface mount soldering. You get a glob of solder going on your board, then you put a little bit of flux on the part that you're trying to secure. Go top and bottom. You place that part where you want it to sit. We will use our tweezers to push it down a bit. Don't want to push down too much because these things can distort pretty easily. And we'll just heat that pad up. Until we're confident that the solder has reflowed. And this is really just to keep it secured while we hit the other one. We'll come back and we'll put a little more solder in there. Of course, I made the mistake of not fluxing this side, so we're going to use our curved tweezers to lift that up. Just make sure we want to get plenty of flux on the FR4, or on the copper that's sitting on the FR4. It's very important. Let me get this fan a little bit better. The flux is advertised as having a decent smell, but yeah, you don't want to breathe it in. So I do have a fume extractor. It's pretty loud. I don't always use it. But at the very least, I always do have a fan going to blow the fumes across my desk. Just a rule of thumb, at least that I tend to use, if you can smell the flux burning, you need more ventilation. You shouldn't smell it. So you can see I'm applying a bit of solder kind of at the edges, and I really just want to make sure that it gets under the joint. Doesn't have to be perfect. Doesn't have to be pretty. It does need to be mechanically strong and electrically effective. So now we'll dump a bit more solder on this, and again, I'm going to kind of go after one of these edges and try to make sure that I have a nice fillet at least 3/4 of the way around this clip. This is overkill. Like, we don't really need to worry about this disconnecting, but I like to make it as secure as possible. Okay, so that's that side. We'll use our scissors to trim the Kapton tape. Use a razor blade. You're probably going to tear it and rip it off, which is going to be a pain because it's going to be really hard to get fresh tape in that spot. Now, this one is going to require a bit more extensive taping because basically this whole area needs to be covered. And just to be sure, you know, the other thing is we need to, let's see, we need to cover this rail too. So we're gonna do a decent amount of taping here, just to make absolutely sure that nothing sneaks by. No electrons, no electrons try to sneak by and short out our voltage rail. All right, so it's gonna need to be trimmed. Ideally, when you're working with Kapton tape, you know, you try not to get it covered in finger grease, whatever, doesn't really matter. It's just not going to be quite as perfect as it could be, but that's fine. I found that electricity and electronics and soldering and everything else, just, you know, it's a lot more forgiving than most people want to admit. Now, I don't do a lot of work with high frequency stuff. You know, these are internally clocked, so, you know, the fastest signal on the board is going to be, you know, measured in the low kilohertz probably. And I'm also not dealing with analog stuff. You know, I'm not dealing with discrete voltage levels and, you know, specific voltage levels. I'm dealing with ons and offs. You know, it's really the simple stuff that I'm doing right now. If you're doing analog design stuff where you have to worry about noise, you know, stuff that's over a couple hundred kilohertz, you know, this probably isn't going to be the best method unless you are a bit more rigorous than I am about following good design practices. But I do a lot of stuff that just makes LEDs blink. You know, it's pretty lame, pretty boring, pretty simple. But that makes it so that there's less things you have to worry about potentially going wrong. So for this one, I think I'm going to do the same thing I did before and hit this pad first. The alignment, if you'll recall, the alignment of the other one is actually pretty important. I don't have a lot of extra width to deal with here, so what I'll do is I'll solder this one down. So I might be missing. I probably need to tape that more. Just realizing that I don't want the. Yeah, we'll see if it works. We'll see if it works. If we have issues, then we'll go back and put on some more tape. I think we'll be fine. Pre-flux this other side. Pre-fluxing stuff near what you're soldering is sometimes of limited utility, just because heat travels really fast along copper, which means, you know, all the flux that you placed so carefully for your future solder joints, you know, still manages to boil off before you get over there. Tin my soldering iron tip just a little bit more so I get a little bit better heat transfer here, because I'm not getting the solder underneath to melt. Right, That is one ugly solder joint, but you know what? It's holding it together right now, and that's all I'm looking for. So now I'm gonna get a nice good final solder joint on this side. And then I'll go back and fix the other one. Most soldering issues, cold solder joints, rosin core joints, you know, whatever, can really be fixed with the application of more heat and either more solder or less solder. So less solder, you use braid; more solder, you use solder. Makes it really easy. I pulled up a little burr on this when I was cutting it, and I want to get better mechanical contact. So I'm just going to squeeze this. There we go. Well, it solidifies. Good enough. That's a severely cold solder joint right now. You can see because it's really just because I didn't heat the surrounding copper enough. But we'll fix that. Put a little more solder. The main reason you want to tin your tip like this, keeps it clean, but it also really improves heat transfer. Even using a decent chisel tip like this, if you don't have any solder on the tip ahead of time, you're still getting point contact, which is really going to minimize, even if you're at 900 degrees, it's really going to minimize how much heat you can transfer. So I don't need all the solder on top of here, but it's there, so I might as well drag my tip across it to make it look decent. There we go, close enough. Time for the switch. So the switch goes right in the middle here. Once we have the switch hooked up, I'm going to drop the batteries in, make sure we're getting 6 volts. Because again, I'm a little nervous that I might not have put enough tape on. And at this point, I didn't put enough tape on. We're going to have some issues because it's going to be hard to desolder these things. Don't stress out about a dirty soldering iron tip. I can clean it with the little metal sponge that came with my iron, but it's just, if you have enough heat, you have enough flux, even if your tip doesn't look perfectly clean, it's probably going to do a great job. So quit stressing about it. All right, so I want to align this so that the bottom 2 pins are on this side and the top 4 pins are on this side. So when the switch is in the up position, just shorts out pins that are already together, but when it's in the bottom position, it turns the circuit on. And I'll use, I want to solder all 6 pins just for structural support, but because of the way this is working, I'm actually using both sides of the switch, so I get a little bonus current handling capacity. I think this switch is rated for 300 milliamps per side, which, if I were maxing out my voltage regulator, that would be one thing, but CR2032s, I think it can only supply 50 milliamps? I don't remember. Depends on a lot of things. There's a good article on Evil Mad Scientist about that, actually, so if you're not familiar with those guys, check it out. Search for CR2032 current capacity. I think it was in the context of LED throwies and whether or not you need to use current limiting resistors with them. Interesting article. And as with all things electrical engineering, it all comes down to reading the data sheet. Always read the data sheet. All right. And which sounds crazy when you're dealing with a quarter-watt resistor or something, but if nothing else, you're designing a PCB. I don't know. I use KiCad and I don't deal with their built-in libraries, so I always just make my own schematic symbols for everything. It's just good practice. At the very least, you need to read the data sheet to make sure you get the footprint right. Even if it's like a standard 0402 part, they probably have a certain way they want you to do it. So might as well follow those instructions. 6.4 volts, fantastic. These are fresh. If I poke them a bit, just want to make sure that I can't jostle them and get. Oh. So when I push down on that, it shorts this battery out. Yep, happens on that one too. Yeah. All right, so what we're gonna do is we're gonna slide a little bit more tape under there just to make sure that even if the batteries get some pressure on them, it doesn't cause a short. That was stupid on my part. I should have been a little bit more careful when I was applying the tape and a little bit more rigorous about it. You know, so it goes. Where's that one shorting out? That's bizarre. Ah, by the edge. You know, you read the data sheet for the batteries, and they probably have a PCB footprint that, you know, shows you exactly where you need to put a solder mask. And of course, I don't have solder masks, so I use Kapton tape. And if you don't put it in the right spots, you're going to have sporadic issues. In this case, you know, the user physically presses down on a button, and you know, if you're playing a board game, some people press down buttons pretty hard after they've been playing board games for a while. So we need to make this thing somewhat bulletproof. Somewhat bulletproof. I'm sure the question will come up, or the comment will come up, that this is, you know, why don't you use Manhattan style, or is this Manhattan style? Manhattan style means you basically use a series of tiny FR4 discs that you punch out, and you use those to suspend parts above a common ground plane. I'm not doing that because I don't really need a common ground plane. You know, if you're doing RF design, if you're building a ham radio or something like that, like everything goes to ground. So it's nice to have ground everywhere. It also minimizes interference, minimizes track length, blah, blah, blah. So I'm not doing that. I'm also, you know, this is, I guess you could consider this like a relative of the dead bug method, but dead bug method is aptly named when you're putting parts upside down and they look like little dead bugs. You know, like dip ICs flipped upside down look like little beetles that are on their backs. And as you will see, I am going to be installing my integrated circuit right side up. So this is not dead bug either. It's a lot more crude than those nicely established and well-respected methods. But I think this is a good compromise. I mean, you know, Manhattan style, I don't think it's necessary in applications like this, where you're not dealing with a high frequency component. And dead bug style, I mean, it's hard to dead bug stuff that has a really fine pin pitch. You know, that was something I tried early on. I dead bugged a quad flat pack, 32 pin quad flat pack, and some TSSOPs that were pretty narrow pin pitch. And it was just hard, you know. I mean, it's hard to solder onto something that is that tiny. It's better, and it ends up being really delicate, you know, even in the best case scenario. So I think this method is a good compromise, and frankly, it's really easy once you've done it a couple times. All right. 6.2 volts. It's interesting when you short out one of these batteries, you know, it drops the voltage for a while by a decent amount. All right, I pushed down on them a bunch. Everything is pretty well insulated, so I am confident that this will get us the reliability that our application requires. All right, so next we're going to install the LDO. You notice that I am doing some testing as I go. It's not something I always do, but it's good. It's good practice. And when you're dealing with a power supply circuit, it's so easy. It's just like, you know what the voltage should be in those spots. Like, just test it. You know, you don't want to have to worry about this stuff once we flip this over, because once we're dealing with like, well, why isn't the LED lighting? We're probably looking at potential firmware issues, and I mean, you don't want to have to mix potential firmware and potential hardware issues if you can avoid it. Trust me, I know. I hate writing. Well, I don't hate it, but I'm not nearly as good at writing firmware as I am doing hardware stuff, which isn't saying much, but it means that I end up having a lot of projects that I physically construct and then they sit around for a long time. Until I have a really rainy day and I really have an empty parts drawer and there's like nothing else for me to do but write firmware for some old project. You see I'm doing a little multi-fluxing here, getting ready for those capacitors. This method, I'll show you a different method of soldering once we get to the 0402 stuff. Sometimes I still do it this way, sometimes I don't. Just really depends. The 0402 components, it's so easy to use too much solder. They're so tiny. So oftentimes I'll just prep the pads, both on the component and on the board, with a little bit of flux, and just make sure I have a reasonably tinned soldering tip, not overly tinned, reasonably tinned. And then I will just touch the soldering iron tip to the part and thank the miracle of capillary action for making everything work. So let's see, refresh my memory. Input side, we want the 6.8, which thank goodness is larger. Thank you, Comet, for making your smaller value capacitors larger. I'm sure there's a reason. I didn't look at the data sheets that closely, but let's say 6.8. Let me just make sure this is right. Yeah, that's 6.8 microfarads and 10 microfarads, so it is correct. You know what? Let me double check. Go back. All right, what I was actually double checking was that the 6.8 does go on the input side, and I verified that that was the case. I know that is a 6.8 microfarad capacitor. I don't know if I trust that this is a 10 microfarad capacitor. It is, all right. Close enough. The thing about having a BK Precision 2709B multimeter is that you learn to turn it off. Because if you don't, it screams at you like 20 minutes later. It just starts beeping. Then it shuts itself off. Pretty funny. All right. In both cases, we want the stripe to face out. We want the stripe to face pins 1 and 3, so those are the positive terminals. Capacitors, at least these tantalum capacitors specifically, a little darker orange stripe indicates the anode. I'm sure that's a standard. I'll bet all yellow tantalum capacitors of this look have that same, follow the same protocol or same standard, but God, always check the polarity. Just look at the data sheet. You should always just look at the data sheet. Every single component you have in your design, you buy it on I buy stuff on DigiKey because DigiKey will ship to me overnight for like normal prices because I'm 2 hours away from them. But I know like Mauser and all the other ones do it too, where it's like whatever you buy, there's a link on the description page for the data sheet. Put it in your shopping cart, click the button, take a look through the data sheet. Just make sure that you're not missing anything. It's very important. Having said that, you'll always have a couple screw ups where like, you thought you read the data sheet. Just kidding, you didn't. So it goes, no worries. You screw something up, you can always fix it. All right. Testing, 5 volts, perfect. What we're going to do is we're going to put a couple little stubs of wire on either side, and those will just wrap around. Obviously, when you're soldering on stuff, take the dang batteries out. No reason to make your life more complicated than it already is, right? So this is how I do quote unquote vias. Is just leave these little stubs of stranded bare wire on either side. Oh, forgot to flux the board. Oh, flux core solder doing its job. For wire and stuff like that, it's just not that critical. What I usually do is I'll just, I will put a dab of flux on the wire. I'll just kind of hold it there. As long as you don't move it too much while it cools, you're good. If you move it too much while it cools, you're just going to get a cold solder joint. Going to be a high resistance joint, or it's not going to work at all, which is not a huge problem because then you can just touch the soldering iron to it. A challenge that everybody runs into with soldering is that you kind of need 3 hands for stuff, because you got to hold your iron, you got to hold your solder, and you got to hold your part. If you're not careful holding the part, you're going to burn your hand. So there's different ways you learn to get around that. One of them is pre-applying the solder to the board, like I did here. You can use like a helping hands type deal. I don't use those as much. My helping hands has been converted into a solder holder, which by the way is a really great use for it once you decide to stop using it for its intended purpose. All right, so those just get folded over, trimmed a little bit, and we'll go ahead and solder them. That'll basically finish off the back side of this board, and then we'll just be able to focus on the fun stuff, the little tiny things, or at least the tinier things. It's really satisfying to build something out of parts that you can barely see. And if you get nothing else out of this video, if you've made it this far, I hope you get out that you can do this. Like, you don't need to have a pick and place and a hot air setup and blah 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 to work with really small parts. Yeah, you're dealing with QFNs, VGAs, anything that has a pad on the bottom that you can't hit with your iron. Yeah, you need hot air, but and hot air and reflow are great time savers. If you're doing a big project with a whole bunch of boards that are all similar and you got a stencil, I mean, it's great for that. Triple your throughput speed. But for little stuff like this, I don't know. I don't think you really need to do that. I think it's actually funner to do it the manual way. All right, so now we get to the really fun one, which is the integrated circuit. I think what we're going to do is we're going to use that method that I kind of alluded to earlier, where we just flux the intended pin locations, drop the chip. Remember, flux is what rips the dirt and oxide layer off right before the solder melts. So flux burns off a couple hundred degrees below the solder, and as it boils away, it pulls all that gunk off. So you want it to be on both the bottom of the pin and the top of the board. Tin my tip. Here we go. I'll just tack it down first. You can see on that one, my iron tip is just about out of solder. So it's time to do a bit of an examination. You can see how all that flux collects in the troughs. It will collect in the trough under the chip, which will present someone could give you some electrical issues on higher performance circuits, but it's not going to be a problem here. And all the flux that comes into those little grooves, I can scrub out. The problem you have is when one of these little dangly guys mixes with the flux and then lodges itself in one of those grooves. So you always want to make sure all your little copper scraps are controlled and disposed of properly, or at least wiped onto the floor. All right, and now kind of use like a modified drag soldering technique, I guess. I mean, you don't have solder mask, so because of that, you got to be a little more careful than you would on a PCB. You can't really just drag from pin to pin. Solder bridges can be more of a pain to deal with this stuff because they don't just like, you can't just like drag them out always. Sometimes you need to actually get the razor blade out and heat the area up with your iron and like really go at it, which is fine. No problem. No problems. No problems. Here we go. One of the reasons this technique never looks as nice as a circuit board is because the solder doesn't have that barrier of solder mask to stop it from flowing like, you know, half an inch away from the chip, which is fine. Ooh, looks like I left my soldering iron at 800 degrees. So there you go, soldering a very small, or actually rather large microcontroller onto a board with an 800 degree iron. I'll bet you it still works, so no worries. All right, now we're going to get to the really tedious stuff. So these are the little bitty parts. 0402 LEDs are very, very thin, which is actually the hardest part. They're 1 millimeter long and 0.6 millimeters wide. But because they're so thin, they're actually kind of hard to grab. And we're going to want all the cathodes, or all the anodes on this side to face that way. So, of course, the LED, you know, the reference mark on the LED is on the bottom, so pull it out. These aren't free either. I mean, they're not crazy expensive, but like, you know, they're not as cheap as like resistors, you know. They can, in low quantities, they're 50 cents a piece, but in the high quantities that I buy them in, they're more like 5 or 10 probably, but still not nothing. So, I don't know if you can see that, but the cathode mark is on that side, which means this side is the anode. And then you drop it, and it's hard to find. Then you start the exercise over again. So, cathode is on that side now, which is ideal. So we're going to flip this over and drop it on the board. Just double check that we're right. Always like triple check polarity. Of course, I forgot to flux the board, so we're going to just gob some flux on there. And we want to do this. I'm going to rotate my board around so I can use my tweezers with my right hand. Confirm cathode is facing that way. Tiny little amount of solder on the iron. I think you'll still be able to see that. I'm using my magnifying glass to really make sure I get in there. And the whole thing is just bathed in flux right now. Oops. Just get that solder all the way to the edge. So these things are so small that like if your groove is too wide, you really have to make your LED into a little bridge, which is kind of a hilarious problem to have. Very ugly, very effective. We're going to be soldering directly onto this little Sharpie mark, so let's see if that works. And it does. So, very nice. Our solder joint on the other side is a little on the chilly side. So, you know what? I'm going to turn my iron down. 800 degrees is way too hot. So, back down to 750. Nice, frigid 750 degree Fahrenheit iron. I try to use the metric system when I can, and being in Minnesota, that means that I have to use both all the time, but I'm stubborn about it. All right, so I'm sure you can't see this on the video monitor, maybe you can, but the cathode side on the front of the LED has a dark mark on it, and we can use that as a reference for the rest of the LEDs. so that we don't have to, you know, flip every single one over and figure out how it's oriented. So that's a pain. So what we're going to want to do, since I'm going to be using my right hand and probably having the board like this for the rest of the time, we're going to want to make sure all the cathodes are facing that way. So we'll rip off a couple of these LEDs. Yes, they do blow away. Do not sneeze. Even you folks watching this on video, if you sneeze. That's how light and tiny these are. Just get the cathode side secured for now. Actually, if they land on your table upside down, you can just push your finger into the LED and they tend to just stick to the end of your finger, and you can then pick them up off of your finger using your tweezers, which takes a little practice. I think if we do a workshop like this someday, we'll use 0603 stuff. It's a little less frustrating. The really funny part is when it, one of these LEDs sticks to the end of your iron, and you're just looking everywhere for it, and you finally like look at the end of your iron and you're like, oh man, that thing is toast. So I've cleaned out my solder braid, or my brass solder sponge occasionally, and I always find a pretty decent amount of tiny little parts in it. The black stuff is the Sharpie, just getting dissolved by the flux. This one's not quite flat, so I'm just going to gently push down on its top. Inevitably, I'll power this up once I've actually written a little firmware for it. And a couple of them won't work. We'll just rip them off the board and put new ones down. If you're dealing with parts this small, you need a lot extra, trust me. If I had my power supply around here, I could set it to 20 milliamps and just probe these and just make sure they all light up. So I might rig something up off camera just to do that. I think I'll get the current limiting resistors on, and then I can just use the 5 volts to do that. Make sure I get a reassuring yellow glow from each one. It's really funny, every once in a while I've had this happen. I'm doing a lot of these. I have like 1 out of 100 or something that, I've blasted it so hard with the soldering iron that I just totally destroy it. Or I mostly destroy it, I don't totally destroy it. And it glows, but it glows very dimly. So it's important to, if you're using this method, really kind of abusing your components, it's important to test stuff a lot more than you would in a production environment. Or maybe I should say test it the same amount as you would in a production environment, more than you would in a normal hobbyist environment. But it's worth mentioning that once these are all soldered down, they're going to be ridiculously strong. And like, you're not, we'll scrub the heck out of them to get the flux residue off, and we won't lose a single one that way. Or I should say, if we do lose a single one that way, it's because of poor soldering. In which case, it's good. If you scrub something off your board because you are too rigorous with your cleaning process, it just means that you need to be more careful when you're soldering them. Again, we're not following NASA workmanship guidelines for soldering, which if you haven't seen the NASA workmanship guidelines for soldering, you should really check them out, because they're a really good thing to read through and just use as a way of getting yourself in the right mindset for, high-end work. Which then you can promptly not follow. So 150 ohm current limiting resistors. Also 0402, can be a little bit more careless with these since they're so unbelievably inexpensive. And those will kind of, how do I do this again? I can't even remember. That one goes in, this one goes on the other side. That's really confusing. But it's fine, it'll work. Get these ones, get these three done first. I think these inner ones, the resistor will actually go on the anode side, which does not make a difference. So I just have to pay more attention when I'm wiring the damn thing up. These are big enough, thick enough that I can do this without using the magnifier, which is probably better for the video. And you may remember that I didn't actually put flux on that side, but at this scale, flux goes everywhere, man. Does not even matter. So, I think what we're going to do is we're going to test those three to start with. So let's load our batteries back up. Power on. And let's see. We'll just temporarily tack these wires down as test wires. And yes, the batteries are still in, but it's fine. You can see what difference it makes if you do not have a tin soldering iron. I am down at a 750 instead of 800, so that's making a little bit of a difference too. But the main reason I wasn't getting any flow there is because I hadn't tinned my soldering iron. I totally borked the insulation up on that wire, but that is okay. Nobody cares. Alright, more solder. Wires, if they're not tinned, even small wires like this, or relatively small wires, they will suck up a lot of solder. They will take all the solder off your soldering iron tip, and they will ask for more. So ground goes to, I'm going to turn my light off so I can really see this. Ground goes to the cathode, which I think we made on that side. No. Yes, there we go. All right. 1, 2, 3. Oh, it's not too much. I guess 580. Yeah, 580 is a little orange. That's fine. I don't mind a little orange. Pop the batteries out, turn the light on, get 7 more resistors on, 4 more resistors on. Hey, my office is in a building that has a number of other companies in it. Some of whom are right next door. And everybody knows that like I have my own office. And they probably think I'm talking to myself, but it's fine. It's fine. Let's rotate this back around. Get those wires out of the way-ish. And the thing to remember, so the way you can really, I mean, there's a lot of dumb things that it's possible to do that I have done many times. But one of the big dumbs you could do is if you're like, you have a 5-volt supply and a bunch of 2-volt LEDs and, you know, some current limiting resistors, and you want to test the LEDs, and I mean, like just touching the wrong pads with those test wires will just destroy these LEDs almost instantaneously. They're so small, you know, they don't have, they really can't handle an out of bounds condition for very long at all. And it's just kind of crappy when that happens after you've gotten everything else to work. So, you know what? I think I see what I need to do. All right, folks, we're going to have our first example of cutting stuff after soldering. I do want the resistors on that side of these LEDs. All I did is I forgot to connect those grooves, so this will be fairly straightforward. You just have to be a little bit more cognizant of not putting too much pressure down and crushing things that are on the other side, but you have a fairly sharp knife, should be fine. And we don't need to continuity check these because I'm pretty sure they're fine, and I'll have multiple LEDs light up if we have a continuity issue. I'll test them with the LEDs. Excellent. Meantime, all 3 LEDs still, or all 3 resistors still sitting on my board, so it's good. You can see in the time that I've been filming this video, I've already switched methods. So now rather than using a tin to iron tip, I've put a bunch of solder down on one of the pads. So yeah, I'm anything but consistent with my methods. Just kind of do what seems like it's right at the time. In this case, you can see that solder joint. I don't know how well you can see this one. There's a little bit more solder, but as long as you get that solder hot enough, it'll tend to flatten out. So you won't have like a huge bridging issue or anything. I do want to be careful not to bridge these resistors. So if I bridge a resistor, it will be exposing an LED to non-current limited 5 volts, or less, I should say less current limited. everything's a little bit current limited, especially with CR 2032 batteries. But I would at the very least be dumping one of those, dumping that tantalum capacitor right across the LED, which I'm sure it would not be excited about. Just to be sure, just want to make sure that these resistors are all, before I forget, left right here. That's interesting. It's got enough bad flux sitting on it that I'm not getting any adhesion to the actual resistor. But you can always put good flux over bad flux. Won't look pretty, but it'll usually work. Except for this time. So we'll just do a little isolated cleaning right there. Flux. Alright, this resistor's gone. Taking them out. New resistor. When that sort of thing happens, you just can't get something to stick. It's just generally just not worth dwelling on. Just rip the damn thing up, throw a new one down. Try to clean things up a little bit in the meantime. But I think I got an extra resistor out. So I mean, if you're dealing with some exotic analog devices, crazy $15 integrated circuit, take your time to recover the dang thing. But when you're dealing with resistors that are $2 per thousand in low quantity, don't sweat it. You'll see that, again, I don't have solder mask, which means in some cases the amount of solder will just completely overwhelm the resistor itself. But as long as the resistor is the only thing that's jumping that gap, 150-ish, dirty connection, so with the lead, so it's not going to look perfect, but yeah, 150. These should all be good because none of the LEDs exploded. I think these are 1% resistors. They should be pretty good. Yeah, looked 1%-ish. Refresh my memory on polarity. Okay. Middle. Boom. Boom. All right. 7 for 7. Not bad. Still recording? Still, yep. Okay. That. All right. All right, so apparently 32 gigabyte SD card fills up pretty quick. So we are back, and all I've really done is deflux this a little bit, not a ton. And I also wrote a quick program that will just turn on all the LEDs by pulling all the anodes high and all the cathodes low, assuming I wire this the way I had originally planned to. I'm going to now solder on the other 7 LEDs and resistors, and we can start wiring. Two, three, four, five, six, 7. really like LEDs. They're just fun. You know, I guess blinky projects are not terribly exciting for some people. You know, they're not the only thing that I do, but I sure do enjoy them. So that's how it goes. Something about little tiny LEDs. Like they're so small that if you don't know what to look for, you won't even notice them on a circuit board. And then it's kind of a fun surprise when one actually lights up on you. So I enjoy that. All right, for these ones, what do we want to do? I don't think I have all of the cuts that I need. I think we're just going to plan to orient them. Let's see. I'm treating this as a mirror image. So we're going to have the cathodes facing the integrated circuit. Shouldn't do it that way. I should have, should not be a mirror image. It's going to be confusing because I have to multiplex stuff. So change the plans, all cathodes face right. Executive decision. Let me make sure that that's the same case on those ones. Dropped an LED, didn't hit the floor, landed outside the anti-static mat. If I don't lose a single LED on this project, that'll potentially be a first. So don't be surprised if this last one goes flying. while I was cleaning the other side off camera, I realized that I could have done some of the multiplexing, specifically tying the cathodes together using PCB traces. It wouldn't have required a great deal of advanced thought, and it just something that escaped me. So, as I had mentioned previously, there's no shame in having a couple extra wires sticking out here and there, but that's going to be the case. They'll be close to the board, so they won't create a delicacy issue. Surprised I'm able to solder over the Sharpie marks so easily. I guess the flux is really just washing that stuff away. Just goes to show how nasty hot flux really is. I wouldn't recommend doing that on anything that you're like selling to someone or sending to space, but for some crap that you're just throwing together, I mean, you can't beat it, right? A little heavy on the solder on that last one. Let's see if we can suck that up. There we go. All right, let's get our resistors in. Try to be consistent with how we do this. So this one resistor will go over to here. Go over there. Need to put another slice right there. Yeah, put another slice there, it won't be fine. These spaces will be unoccupied as they are over here. Get the first 4 in. Again, the solder's got to come from somewhere. In this case, I'm pre-applying it to the board. The LEDs, I was pre-applying it to the tip of the iron. But if you do neither of those, you either need to figure out a way to, well, basically you need to figure out a way to hold the part, which is can be a real issue with surface mount stuff. I mean, the only way to hold these things is with very fine needle point tweezers. I say very fine because I've been through a couple different needle point tweezers, and these are the ones that happen to work. They're nothing fancy. They're just kind of just no-name brand needle point tweezers that I found on DigiKey. But they've worked for a couple of years, and will probably work for a couple more, as long as I don't bend the tips up too much. I tend to use tweezers for drilling like little tiny holes in cardboard, so I do go through them because I don't always use the right tool for the right job. Before we test those, I'm going to pull this out and get that last little slice in that we were speaking of earlier, and we'll be able to get the last resistors on. This is where it gets dicey because really my right hand is pretty worthless. So I need to use my left hand for the razor, but when you're on the far side of the board, you're pretty close to your thumb, and I guess that would just make my right hand more worthless. So it probably wouldn't be a huge loss, but you still want to be careful. All right, gonna need one more 150 ohm resistor. think one thing that would be cool is if you press the button and everything kind of lights up. It'll kind of light up, all of them will light up a little bit dim because you'll be cycling through them so quickly. But I think it'd be cool if when you release the button, there's a little bit of inertia. So it kind of winds down, looks like the, when you let go of the button, it's kind of slowing down instead of immediately stopping. So I think that's something that I'll try to build into the firmware, which I will probably write soon after testing this. We'll do that offline, and then we'll get one final upload and then rip the programming leads off. I like Atmel processors for any of a number of reasons, one of which is that I use a Adafruit USB Tiny ISP and GCC tool chain, so everything's open source, everything's done from the Linux command line, everything's super simple, super lightweight, which makes it really easy for me to get my head around, which is really important. All right, so I did cathodes on the right, so this should be the right polarity. 1, 2, 3, 4, 5, 6, 7. Excellent. LEDs, 14 LEDs successfully soldered. Very nice. I think the next thing we're going to do, we'll get the switch attached, we'll get the bypass capacitor attached, we'll get the pull-down resistor attached. Then we will be able to switch gears a little bit. My fan just died. So let's hold for 1 second while I figure out a way to plug that in. All right, grabbed a USB cable, plug fan into computer, which is currently charged. So stealing power from one thing to power something else, pretty standard. That is not power and ground. Wow, glad I double checked, huh? This is power and ground. Tiny ceramic capacitors are the easiest of the tiny components to solder because they have a square cross section, which means there are 4 acceptable orientations as opposed to 1. They're also very cheap, as with a lot of the non-semiconductor parts. I mean, when I say cheap, I mean like $1 per 10,000 cheap. Bypass capacitors, basically trying to keep the microcontroller from browning out during it while it suddenly draws significant amounts of current for very short periods of time. So they just act as like a tiny local reservoir. Because of that, you want them to be really close to the microcontroller. So that one's a couple millimeters away. Should be fine. Should get the job done. What else do we have in our component supply? We have 10K resistors, and we have a switch, which I believe was missing, so we'll just pull another one out of the package. Little turn up. Stuff always turns up. I got a place for it, put it back in its place. That's why I always want to have extra stuff. I like these switches. They're purple. Makes them awesome. They're also waterproof, so you can use them for, you can wash the boards afterwards and not have to worry, which is nice. So, let's see, we're switching across there. Why don't we just solder it on? We'll figure out the pull down stuff later. And again, the switch would work now, you know, because we're just crossing these two connections, but for mechanical strength, of course, we will solder all four. You solder stuff like this down to a board, and it is not going to go anywhere. If you solder all the pins, you can solder most of the pins. It's just going to be so strong, which is really awesome, especially this low profile stuff. I mean, this switch is just, you know, you could smack it pretty hard and it would be fine. So one side of the switch will say, will feed power to the outside, and then the inside we'll use as our signal, which means that we need to also pull the inside down to ground. To do that, we will make our final cut, hopefully. No problem, no problem. Cut a little bit into the other side, but I have to cut a little bit more for it to actually cause an electrical issue. It's just going to be aesthetically challenged now. So let's get that 10K going. 10K is just it's usually a good size for a pull down. I mean, you want to read your data sheet. You know, data sheet will give you ways of calculating a good pull down, and generally, the weaker the pull down, you know, you use a 100K pull down, it's obviously going to consume less power, but it's not going to be as immune to noise, and so there's a lot of things to consider if you're like trying to optimize the size of a pull down, just like trying to optimize the bypass capacitor or anything else. And in a lot of applications, it's like, you know, you only have so much time in the day. Use the 10K, use the 0.1 microfarad, it's going to work. All right, so I could actually connect power there, or connect the ground there, connect power there, and we could connect signal either there or there. We kind of have space for either option. I think what we're going to do now, ground and power. Let me just make sure. All right, ground is 14. So those are on the right side by a wonderful coincidence. I know they're a little ugly on this side. You know, it's not a huge deal. We'll just be able to tack those right down there. If you don't own a pair of automatic wire strippers, that's fine. I suggest purchasing some. Definitely important when you're like I'm doing a project that involves a lot of little fiddly connectors that I have to crimp and assemble, which I now have someone else do, which is great, but I've still made a couple hundred of them myself. It required stripping a lot of these wires to exactly the same length very consistently every time, and they were important to have. And I found that I just use them for everything now. These were, I think they were $90. I'm sure you can find cheaper ones. I didn't. I used the nice ones. And they have been a fantastic investment. I can do most wires that I deal with. I mean, it'll do down to I think 28, maybe 30. So it's not going to do the wire wrap stuff, but you do that with a fingernail anyways. And I think they go up to like 14. Adjustable length, and just really well designed. So, you know, they're always going to be, once I dial them in, once I get them to the right length, they're always going to do that length, very consistently and very, very kindly to the wire. I don't have to worry about damaging the wire. In an application like this, I can just go snap, snap, and I'm done. I don't have to worry about putting strain on the wire and like ripping it out. You know, it's just not a concern. All right, I shouldn't have done those yet, but I did, so we're gonna deal with that. So I'm gonna have to work around those wires now, but that's fine. That's no problem. You know what? No, I'm gonna pull them up. No. They're so nicely attached, though. I think I'll be able to. Well, it'll make it a little more challenging. I'll just work around them. So, anodes on this side. Anode, 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 anode. I want to connect this anode to that anode to that anode, so on and so forth. Connect all those to the port A registers along the top. 0, 1, 2, 3, 4, 5, 6. And then I want to connect all the cathodes on the other side of the resistors, like this. 1, 2, 3, 4, 5, 6, 7. Those will all be tied together, and those will connect over here. So the first thing I'm going to do is tie those cathodes together. And the way I'm going to do that is by doing them in groups. And I will flip-flop again, and I'm going to remove these wires, probably entirely, actually, just to get them out of the way. So clean and easy to desolder stuff that if it's in your way, get it out of your way, man. It's not worth the trouble. Look how long it's taken to heat up, just because I don't have much solder on my iron tip, and you know it's at 750. But that's fine. All right. Actually going to start with this side. But that's how it goes. So we will start by connecting the little fiddly bits that I shouldn't have disconnected in the first place, but I did. I'll show you how to do that. It's real easy. I think what we're going to do, we're just going to tin a length of this wire just so we don't have to worry about it. Tinning wire is easy, but you got to do it right. Like, you don't want to just try to dip this in solder unless you're also dipping it in flux, because you really anything that solder is attached to needs flux. Flux is very important. Now, I think we're just going to throw down some blobs. Throw down some blobs. And there's a little scrap that picked up. Just deal with that. A little bit of messiness. I'm gonna use my tweezers. So sometimes you can hold stuff by hand. More often than not, I do it because I'm impatient. But tweezers, which you can like really brace against something, are gonna be a lot more stable. And again, I mean, and this is where the different solder types will you'll really notice them. But you know, solder's an alloy. It's not a pure metal. And depending on how far an alloy is away from what's called its eutectic, you'll go through this range where it's kind of slushy. So you're between what are called the solidus and the liquidus lines. And as long as you're in between those points, some percentage of the alloy will be liquid and some of it will be solid. It'll be like a thermodynamic equilibrium in a slushy state. And again, depending on the alloy, the temperature range between the solidus and the liquidus varies. In a eutectic alloy, which 6337 tin lead is very close to being a eutectic of tin and lead. That's almost nothing, which is why 6337 tin lead solder solidifies almost instantly. 6040, which is more common, still is very close to instantaneous. This lead-free stuff, I haven't looked at a phase diagram of it, but just through visual observation, I can only assume that the distance in terms of temperature between the solidus and liquidus line for this alloy is higher than it is for lead solder. And between that and the higher temperature you have to operate at, I mean, those are the two reasons people really don't like lead-free solder. The excuse you always hear are what are called tin whiskers, which is a strange growth phenomenon that shows up at the microscopic level over time that causes performance issues with things like BGA packages. Basically, the bits of tin will like kind of grow out in strange ways and eventually short the thing out, which is relevant when you're dealing with like a 0.5 pitch BGA package or something. Fact of the matter is, you know, an application like this, you know, tin whiskers are not they're not going to be the failure mode. The failure mode is going to be I step on it, or I throw it away in 20 years. You know, which is why like the Navy took so long to go full RoHS. It's because they were worried that they would get a tin whisker problem. Well, there's probably a lot of reasons, but what I heard is one of the reasons is you know, 20 years after putting together a board, when it's 3 miles under the ocean in the middle of nowhere, you know, suddenly a tin whisker would reach its destination and short something out, and they couldn't have that risk. I make products. I make educational products. I make desktop products that students put their hands on, and to save money and save complication, and because they look cool, I don't use an enclosure for those products, which means that I have middle schoolers that are handling bare circuit boards that I've manufactured. And there's nothing wrong with that, but it means that I'm really serious about going lead free. You can't mess with lead around developing brains. Now, if you are putting your circuit boards in an enclosure, or they will just, you know, potentially never see human hands, it's not a big deal. But you know, for me, it was a really easy decision. And once I made that decision, I just changed my methods and was surprised by how easy it actually is. It's really not a huge deal. All right, so I think I'm going to switch over to the magnet wire. You know what? Not for the cathodes. I don't think I want to for the cathodes. I think the current's still going to be might be a little high for that. I suppose I should consult a wiring chart. All right, I'm gonna go check the rating on 34 gauge wire. All right, I consulted some internet charts, and I do not believe it will be an issue to use this wire for multiplexing. There's like something about power transmission versus chassis wiring, and one of them's more conservative than others, and I'm just not going to worry about it. This is not going to catch anything on fire, so no worries. So with this stuff, you can basically just tin your iron, touch the wire. And you kind of do it a couple times, and it's in pretty good shape. I'm going to try to be fancy actually, and do one length of wire and then tack it down in the middle right here. See if we can do that. I'm going to use a little bit of flux, because when that polyurethane insulation burns away, it'll give us a little debris. And flux is magic, obviously. And I'm just gonna lift this up just a tiny bit, so that even if I shed some insulation elsewhere, it doesn't cause an issue. There we go. The nice thing about using this really fine gauge wire, of course, is that it's a lot harder to block the LEDs, which is what I don't want to do. And again, when I'm all done with this, have it all dialed in, and don't think I'm going to have to solder on it anymore, I'm going to spray it with a couple coats of poly. And I'll lift the wires up again before I do that. Just make sure that they're ever so slightly above the level of the circuit board. Not that far, but just enough. Yeah, this is pretty sloppy. Hopefully nobody that made it this far in the video had any illusions about the cleanliness of this methodology. Alright. Now what I'm going to do is basically going to go around and I'm going to put little dollops of solder on all the anodes of all the LEDs. Big pads to work with. Love it. One's a little tight. Remember, all the anodes have to connect to all the other anodes on the other side of the similarly pipped dice location. Flux. So defluxing at this point is going to be a little bit more difficult. I'm going to need to be a little more careful, just because I have so much fine wire all of a sudden. Just leave myself a little bit extra. Hoping I can just hold the wire by hand because it's just so much faster. It's thin enough gauge that it really doesn't conduct heat very fast or very much heat. But it is very important that I don't get a rosin core or a polyurethane gunk core joint. So I'm trying to be very cognizant of that. So what I'm trying to do is just really give the flux time to do its work. Really hitting it with enough heat, and then when I stretch the wire out like this, I've been trying to put a little bit of extra stress on the wire, like not an inordinate amount, but enough that I can really tell if something's funky. What's interesting is that when you're doing stuff like this, putting together a multiplex display like this, in my experience, short circuits will not show up as dead LEDs. They will show up as LEDs that are lit when you don't want them to be lit. So I have a program that I put together off camera that's very, very simple. All it does is light up all the LEDs. But what I'll probably do before I actually rate any more real firmware for the thing is I'll just upload code that only lights one LED at a time, and then either have it toggle when I hit the switch, or more likely just modify the firmware and upload it again and do that 14 times. Just so I can make sure that I have individual control of each LED. What you don't want to do with a multiplex project is have an error like that you haven't identified, because it's going to be really, really frustrating to track down. So part of this method is about being okay with its impreciseness and kind of embracing that. I mean, you can take your time and make every cut square and make every wire the same length and route everything really carefully. And I think one of the neat things about it is that the printed circuit boards are all, I mean, like, or the circuit boards that you're making, it's going to be unique. It's going to look strange, and I mean, it's kind of an artsy thing, I guess, but that's okay. You can take your time and make it perfect if you want also, but I'm trying to make a little dice thing. I'd rather spend my time playing board games than making it look perfect. All right. So now I have cathodes and anodes on that side connected. I think what I'm going to do is kind of move these wires off to one side. Wire's pretty durable. I mean, like, you want to be somewhat careful with it, you know, but you can push it around a decent amount. What you really want to make sure, with this stuff, you're not stripping it, which means it's not going to get nicked at the, as stripped wire will often. It's often how it gets damaged, which is nice. So back to this enormous wire. Give it a little tin. And I did lose a couple strands from this wire, but whatever. I'm using it for like 2mm bridges, essentially. Alright, it's a lot of solder, but it's okay. It's not okay. I am bridging right now. So to fix that, ideally I'm able to locate my solder braid, but it doesn't look like that's going to be the case. Yeah, I had a short to ground, caused all sorts of problems. So right there I flipped my soldering iron over because I had a little more solder left on the other side. I just wanted enough so I could get good thermal connection. So rather than trying to find my solder braid, I'm just going to cut that a little bit out. Remember, solder is a very weak, soft metal. So if you have a little isolated part of it, sometimes you can just slice it out. Alright, a lot sloppier than the other time, but it will get the job done. Okay, gotta be careful with this one. These three are in a row, but these ones kind of dance around a little bit. So we're gonna do that with the magnet wire, I think. I'm gonna try to do something a little fancy here. I'm gonna try to use one piece of magnet wire and string it between a bunch of them, which is dumb, but should be fun. I should have just kept that other piece of magnet wire on the other side. Should have just kept it going. Alright, so this little piece should be connected to all the cathodes on that side. Let's just double check that. A lot of flux floating around on there, so don't get great connections with the multimeter, but we're in good shape as far as I can tell. So here's the question: is it possible to just loop these around? Really interesting. So jump from anode to microcontroller to the next anode. Let's see. See what the resistance of some of these is too. I'm just kind of curious. And again, we're going to be going through flux too, so that's less than ideal. But 0.1 ohms, 0.1 ohms, 0.1 ohms, 0.1. Yeah, 0.1 or 0.2. All right, that's fine. No worries there. So, this. Perfect. What I often do if I have a whole bunch of things to connect like this is I'll just do them wherever it's convenient and then either trace everything back later or just test it, see where stuff lands. The really important thing is that, well, a lot of things can be fixed in software, but it's important that like this one and this one correlate. So those two. We're going to drop here. See if we can get this without any flux. It's the anode for that far one right there, so it's going to go to that one that's got the little mark on it. Come on. So this is another slightly more risky technique where you hold something down with your iron, grab the solder, apply the solder, pull the solder away, grab the tweezers. Boom. Easy. Ish. Easy-ish, I would say. Ooh, still got my batteries in. You know, I'm not gonna worry about that, I don't think. Yeah, we should be fine. You know what? Yeah, I'm gonna take my batteries out. Even though we're hardly putting any heat into this board at this point, it's just good practice to not leave your batteries in. So that's the cathode. These will all go to these top ones. So starting with that one, which is the other low one. Flux in there. It's good to have all this stuff kind of right in front of you. So when you're like, oh, I don't want to move my soldering iron because I don't want that wire to lift up, you can still grab your flux because you know that it's going to need some. Yeah, so I like these thin wires because they're going to squish down real nice. Excellent. It'd be easy to move them out of the way of the dice pips and just smush them down. You know, I'm gonna wrap this guy around the ice. No, not gonna do that. It's going over like so. The wires will kind of weave in and out of each other a little bit, which is fine. You just want to make sure that where they're crossing each other, you haven't heated up enough to burn the insulation out on both wires. I think we'll be okay. We will be running some additional tests. This guy's really getting in the way. All right, he's a cathode, so we want him to jump into PB0. Oh, it's right there. All right, excellent. Easy. When you're dealing with this part, you just want to be careful around bridges. I want when I'm connecting to the pins that aren't at the end like this, I always try to run them vertical like this, or I guess perpendicular to or parallel with the cut. You don't want to be perpendicular to it to really want to avoid the risk of bridging. Again, bridging's pretty easy to see, like you'll know what's happening, you can fix it, it's just a pain. So that's dice 1 cathode on PB1. Now, let's see, we'll do the far left one, left middle, pip. Yeah, dice spots, I believe they're called pips, P-I-P. Strange, but so it goes. I think I'm going to want all of these to start high and then curve around low. You don't want that. You don't want them to curve too sharp. You don't want to kink the wire. But you know, minimum bend radius for this stuff is pretty low, so I'm not going to worry too much. Notice that, like, connection to connection, my methodology changes. It's really just a feeling sort of thing. There's so many different ways to get the same job done. In terms of like when you add the solder and when you add the flux, or if you just depend on the flux core and the solder, you just kind of get a feel for what's the right method for the right job as you learn. And for this one, I think I'm just gonna blob it with some flux and hit it with the iron. Now hold it down. Holding stuff down with the iron can be a little challenging. This wire is very thin, but it's like not infinitely thin. So you do have to hit it level with the iron, or it'll slip to one side or the other. All right. Middle anode, middle LED. And a little spillover solder. I'm gonna just tin these pads. Don't have to worry about that anymore. I'm actually gonna tin this wire too. You can see how the solder initially doesn't want to stick to the wire. Maybe you can't see that actually, but I promise it's the case. Iron was getting a little crusty even by my relatively lax standards. as you go, you cut more and more wires, and it'll be easier to manage the wires, but it'll be harder to get them to actually land where you want them to land, because things get a little crowded as you go. Top left. Wait, what I really don't want any wires hanging off the board. Not because it looks bad. It's going to look bad no matter what. But because it's going to be a durability issue. There's one thing I don't like. It's when my stuff breaks after I've been actually using it for a while. Like, I want to throw this in my, Settlers of Catan box and use it. At least for a little while. Don't want it to just self-destruct. Alright, so that's the far, what did I say, far left? Yeah. Alright, 2 to go. Not bad at all. Plenty of space, plenty of time, no issues. Alright, we're going to be on high solder bridge alert for that joint in particular. Let's go ahead and test it right now. Good shape. Those little beeps that you heard were me touching it where I could tell that was happening. Oh, this one's for this guy down here. All right, we're not going to be in perfect order, but I think we've been good about making sure left and right correspond to each other, which is really the important part. We can figure out pip specifics later, just as long as we have pip consistency. Pip consistency. Yeah, I'm being a little sloppy with the magnet wire, but I just don't think it's going to be a problem. One of the more important things that I've learned is that stuff's more forgiving than a lot of people give it credit for. I mean, like, you gotta do your homework and like do your Ohm's law and stuff, and not overpower stuff and not burn yourself and get rid of solder bridges. But like, I don't know, things like anti-static, like people that are really concerned about static. It's just not that big a deal. At least with the stuff that I deal with. Your mileage may vary, of course. I think we're just going to do this one straight across. See if we can get away with that and not bridge. All right, really obvious bridge right there. There we go. And this is that's the kind of wire that I want to be careful of, is one that really kind of comes off the edge. That's a problem. Kind of cheat your way into it, I guess. All right. The wire's got a little bit more bend on it than is probably good, but it's gonna work, so it's fine. Like I said, I'm gonna poly this thing pretty good at some point. All right. The last connections to make. We got the switch, and we have this other cathode. I think I'm just going to pick it up right here, just an easy spot. Actually, first thing I'm going to do is get it secured to PD1. So I have the luxury of choosing what order I connect it in. Do it that way. It'd be easier. So if I were to do this again, I think some of this multiplexing, some of the wiring, I think could be accomplished with PCB traces. That would save a small amount of wiring, but you know, any amount is good. Oh, I'll just pick it up right here. Perfect. Ooh, actually, in this case, I'm going to give myself a little slack because I still have a couple wires to solder in right here. I have the switch, push button switch input, and I have the reset line, which I have space to spare, but as I've said a couple times, I have a tendency to minimize space at the expense of frustration and reliability. This is not working at all. Come on. All right. I think that's it. Before I get the switch secured, I think I'm going to test these LEDs. The way I will do that is by temporarily resoldering my power and ground wires back on. Maybe permanently, we'll see. Oh, I know what I need to get. Just a second. All right, how could I be so foolish? Ground has to be black. Or negative, I suppose, has to be black. Make it nice and obvious which is which. Nice. Alright, throw some batteries in. Power is on. So now, theoretically, should be able to connect the negative to these. And then, right. We're 7 for 7. Not going to do any more testing like that because I'm at a high risk of accidentally shorting something out, and pretty sure the microcontroller doesn't like it when I power its pins, but I don't power it. So we will change that presently. Make sure these power wires comfortably sit to one side of the LEDs. I really don't want that to affect viewing angle. This wire, it's Alpha Wire Eco Wire Plus. It's a decent wire. I like the matte finish on it, but the insulation, as with many plastic insulated wires, is a little bit wimpy. So like you kind of got to be careful soldering it. It's okay because it's inevitable that you're going to melt the insulation as you're soldering it, depending on how much you strip it back. But you want to be sure that you're squeezing the insulation with a pair of tweezers, you squeeze it in a place that you're okay with, getting a distortion in. Or if you don't want that, grab the bare wire with the tweezers. The other thing to know with wire like this when you're soldering it is that if the wire is under a lot of strain, if you're pushing the wire off to one side and you heat it up, you do that, too much, you can really blow the wire out. And by blow it out, I mean you'll actually get a bit of these strands will pop out of the side of the wire and really bork up your insulation pretty badly. So something we want to try to avoid here. This might be a little dicey. I want to lift up that wire. So I want to nail the ground right on the outside right here, I think. Yeah, that signal wire might be a little close for that, but we will attempt it and report back, see if it works. going to be a job for a small wire strip, plenty of flux, and a light touch if that's possible. I won't tin the wire. Kind of looked like it moved a little bit during cooling, but I think we're in good shape. Yep, and now I can just scooch the wire over here a bit. Oh man, the wire's just a little bit too long. That's dumb. All right, it's gotta be right. So what I'm gonna do is I'm actually gonna desolder the wire from right here, trim off the excess, and then solder it in a straight line from the end. You'll see what I'm talking about in a second. Always have 2 tweezers on your desk, so when you drop one, you don't have to take your soldering iron off the wire. You can remove it. You notice that I'm pretty fearless about just grabbing wires pretty soon after they get soldered. They just lose their heat pretty quickly. I mean, stuff will be a little bit hot, but so small, just, you know, you're probably not going to get burned. Oh. Then every once in a while, the wire stripper just totally fails. I think I didn't get a straight shot with that, but yeah, basically that nicks the wire far back enough that, you know what, I think I can still rescue this. Yeah, I think that will be fine. No, it's not quite long enough. I'm just gonna have to take it off. It's tempting to make that work, but there was like a millimeter where I didn't have insulation under it, and it would be hovering over another pad. I really want to be able to squish everything down with my thumb and then polyurethane the whole deal. And that way I would be relying on having a little airspace, just a recipe for trouble. However, I can use that piece of wire to cut another piece of wire just ever so slightly longer. Ever so slightly longer being the key here. Yes, it is much longer. Excellent. Normally you want to heat both the thing you're soldering and the base. In this case, I'm pumping most of the heat into the wire. And because of that, I'm not getting a great joint on the other side, but I think it's going to be fine. I really don't want to put too much heat onto that other side because I don't want to risk torching the insulation on this wire. Because he jumps from here all the way over. I just don't want to have to deal with that again. All right. G, see if we can burn that away with the flux. Yeah. Not super clean, but you know, it'll get the job done. Yeah. Takes that industrial grade Sharpie right off. No problem. All right. I think that's looking pretty good. All we need to do is get the switch wired. So the switch has 3 wires feeding it. One is a power, one is ground, one is a signal. So we have a pull down resistor local to the switch. So the ground is going to be the most difficult because it's got the most stuff around it. So we'll do that one first. Fortunately, there's a Mondo Blob piece of solder right here that we can take advantage of. And pull down, so we need to be on the other side of that resistor, so we'll cross over like that. Leave the excess attached for right now. So we have something to hang on to. All right, we'll get our power connection. You know what, I think we can, yeah, these guys can get moved a little bit. Thread it under there and take advantage of this giant Mondo blob of solder that's just sitting there. This is power, goes the other side, over here. And these wires, you know, I'm not stretching them like completely taut, but I'm trying to keep them pretty tight. I mean, it's a pretty narrow band that I'm working with because I don't want them to flop all around. You know, the poly will help that. The other thing is, if I stretch them really taut, I'll probably make the mistake of stretching one taut right over an LED, which it's thin wire, but they're tiny LEDs. It doesn't take much to block their light. So just gotta be aware of that. It's nothing like having a nicely routed, perfectly soldered, electrically working wire that just is like blocking an LED. You know, it happens more often than I like to admit. All right. Signal wire for the switch, and then we'll be good. And we'll just need to get the programming leads connected. Dump that test program in and make sure all the LEDs light. They advertise the AT Tiny 44 as having 12 I/O lines. To use it with 12 I/O lines, you need to designate PB3, which is the reset line, as an I/O line. As you can imagine, to do that, you have to set a fuse, which basically makes the reset line no longer work, which means you need a special programmer if you ever want to reuse the board, or you screw up the firmware, or you do something like that, which are all, and I never want to get myself in a situation where I can't re-flash firmware. That seems like a terrible idea. So I consider the ATtiny44 to be a chip that has 11 I/O lines, which is still more than enough for my purposes. So PA7 is that. Yeah, we'll just snake him right through there. It's third from the side. Again, before you take the soldering iron off, make sure that wire's secure. All right, that's it for everything that's going to be permanently wired. So this is what it's going to look like. This switch sits a little high, so I think I am going to need to put some kind of legs on this thing. What those look like is kind of to be determined. Probably be easy to just do little chunks of FR4. The problem with soldering to this is that, I could solder to this ground point right here. I could put a leg coming off here, but then if I put a leg coming off here, you just want to make sure you don't use it on a metal table. Not sure that's really an issue though. Yeah, I'm gonna give that some thought. For right now, I think we're gonna get our programming leads attached so we can test this dang thing and make sure it actually works. It's still very much an open question. So programming leads, obviously, they just have to be connected long enough to test the thing. There's 6 of them. You got a master out, slave in, master in, slave out, SCK, reset, voltage, and ground. And what I'll probably do is just connect 5 of those and set my programmer to allow this power supply to power the chip, because it's one less. Let's put the reset line on there. It's not pretty, but it'll work. Give yourself plenty of extra wire. Master out, slave in is pin 7. And oftentimes when I do stuff like this and I'm like done programming it, I don't even bother to desolder the wires. I just clip them. Because who cares, It's fine. My programmer's ribbon cable is on its last legs, and that's something I gotta watch. When you're testing a new circuit like this and you try to program it and it says like, oh, chip not found, it's really, it'd just be kind of frustrating if it you eventually figure out, oh, that's chip is found. It's it's not that. It's a it's an issue with the connection. Let's see. Let's get our ground connection. master in slave out is pin 8. This is a jumbled mess in here, so I'm just going to trace pin 8. And that goes back to here. All right, it's an easier pad to get. All right, master in, slave out, and finally clock, CK, pin 9. Pin 9, also a difficult one to trace, because there's a lot of stuff going on here, a lot of things not soldered down, stuck down with flux. Alright, good move, Zach. Put SCK right in the middle. Or I guess the left. Can I pick it up from that side? Yeah, I'll pick it up from this side. Just to verify. Yeah. Of course, this is the time when I will accidentally desolder an LED or bridge something that I worked on like an hour ago. So, just want to be careful. See how impatient I am, like I'm not even using my vise. Pretty typical for towards the end of a project. Oh, left the multimeter on. I really want to just like tear the buzzer out of that thing, but I need the buzzer. It's the continuity buzzer. So it goes. All right, time for the vise. And I think it's bad practice to put a load on like some of these pins while you're programming. So we'll see if that becomes an issue. I mean, I'm using MOSI and SCK and MISO. I'm using all 3 of those for LEDs, so we'll see what happens. All right, let me go grab my programmer. All right, so reusing some NeuroTinker stuff, specifically my programmer. This is for my version 9 boards, which if for some reason you're following that project, you'll know version 9 boards had all sorts of problems. Like they never worked. They had a trace that covered like a track, and I don't know, it was just a disaster. But I made 3 Pogo boards. And they're conveniently labeled, so I've just been using them, repurposing them as in-circuit programmers. Let's see, reset line. Come on, buddy. Is that handful slug of insulation, really doesn't want to burn off. Alright, MO, or MISO, master in, slave out, which is pin 8. How did I do MISO again? You know what, let's do a different one. Let's do ground. It's easy. Of course, I don't have a wire connected to that. It's okay. You know what? How many times do I twist this around? Dumb. Fine, I'll play that way. So let's see. Ground. Gross. Reset. Not sure how good that electrical connection is, but I think it will suffice for telling the microcontroller to reset. Alright, what is this one? I think this is the CK pin 9. The CK. Not the best way to solder these things. I mean, like the reason when you wrap them around the post, the insulation just like does not want to leave, and then you just use more solder, and it's just really ugly. But we won't look too close. This one is 7 MOSI master out slave in. Goes way down here at the bottom, and we can use the process of elimination for master in, slave out. these are the 6 Atmel in-circuit programming pins. So that's the protocol. Very simple, designed to be used while the processor is, well, in circuit. And like I had mentioned sometime earlier, you know, I use the open source tool chain that Adafruit has on their website, you know, affiliated with their USB Tiny ISP, which is the programmer that I use. I think there's plenty of other ones that'll work too. That's the method that I use to compile and send programs to Atmel processors. It's very easy. Just did not connect. I think we might have to do some continuity checks on this, which is almost embarrassing. But there we go. But first, just see if we can get it to work. So first we just test it, see if it works. If it works, then we don't have to do any other tests. Again, we got a nice little failure mode right here because well, it's a long story. Basically, I broke it. I messed it up. It's fine. Plug that in. We did not supply power. We're not supplying power through this, so we want to take the jumper out. Put the batteries in. Make sure the power is on. Check for smoke. See if the chip gets hot. Does not seem to be getting hot. It's good. All right. Just get my computer going. Green light there. Initialization failed. All right. Do some continuity checks. Okay, it's 9. It's 10. 7. Well, those all look right. I really need to get a new ribbon cable connectors for this because I went through this last time. Total pain. Not good, not good. Just make sure we're getting power to the processor. 5 volts. Ha! There we go. Looks like it's working. All right, I think that's as far as I'm going to get on this video. I'm going to write a little bit of code for this thing. See if we can get it working better. But so far, so good. All right, I think I got this where I want it. Really simple firmware, but I have disconnected the programming cables, so that'll be it for a while. You turn it on, it starts at 5. I should have changed that so it started at 7, so you knew it was time to roll. And then as long as you're holding down this button, it lights up all 7, and then it gives you a pseudo-random dice roll. What it's actually doing is, as long as this button's held down, it's continuously cycling 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6 on the left dice, and then every time that resets, it'll increment the right dice by 1. So 1, 2, 3, 4, 5, 6, 1, 1, 2, 3, 4, 5, 6, 2, 1, 2, 3, 4, 5, 6, 3. And this operates at the full speed of the processor, so you know, even a really fast press, you're not going to get the same number, ideally. Haven't checked it for randomness, but it should be pretty much as random as it needs to be for a pocket-sized dice game. You know, the main regret, I think, is that these LEDs aren't as bright as they could be. So there's other models in the Pico LED series that put out quite a few more millicandles, might be better suited for this, but then again, when you're playing dice, you're usually in a darker room. So I think this worked out pretty well. I'm going to clean it up a little bit, give it a coat of poly, and call it done. Thanks for watching.